Yes, so thank you all for coming here. Just very briefly about my background, just that you know, I'm not one of those interesting data scientists with a lot of computer background, etc. I'm one from the other way, mathematical statistics, and then found out that computing and R is really fun and started doing more of that. I'm from Aalborg in Denmark, and I'm one of the developers of the SPATStat package, which is a rather large package for handling or analyzing spatial point patterns. And this is really why I got into this S2 library I'll tell you a little bit about. Because we wanted to, at the moment, SPATStat, like almost all other spatial stuff in R, requires that you have projected flat coordinates. Like there's almost nothing that does, there's the geosphere package that will calculate distances and areas of some things, but otherwise almost everything is on the flat surface. So you need to project things first. And I guess all the people here probably know that. Less experienced users get annoyed by this, and we wanted to really, and of course there's also like a methodological issue about that if you have really large distances and a global data set, you are in the sphere, you can't project it and just pretend that it's flat. So we wanted to do that for some of our spatial point pattern analysis, so we needed to be able to calculate stuff on the sphere. And I thought, why should I implement this from scratch? Because I would probably not be so good at that. So I was Googling around, and mysteriously hidden was this thing called S2. So the S2 is for the mathematical notation of the sphere. And it's something that Google has developed and open sourced it and put it out there. And now it looks like they're not touching it. I think they use it in production and probably develop it on their own or whatever, but they have that open source part. And it's used in different companies like Uber and Foursquare and whatever. It really has some nice capabilities. It's a little bit hard to find a lot of, well, actually in the last year or so, there's been a few blog posts about how does this actually work and how can we use it. And what I did was to download the source code and then put it into the R framework. And this is not a system library. Like you don't just install, like find an exe installer somewhere online and install it on your Windows machine, or sudo apt-get install on Linux. You need to compile it from scratch. So I've taken the source and put it into an R package, and then I had to like clean up a few things because it wouldn't compile with the R tool chain and all this fun. And in the end, it works. At least it appears to work. Nothing is segfaulting or anything anymore. So I'm happy. Yes, and it's also been ported to other languages. So I guess in this forum it's kind of stupid to say if you don't like R, you can go for Go or Python or whatever. But now we want it in R also. And a main thing is that they have this spatial index. And I'll try to explain how this is constructed. And the first thing you do is that you take your sphere. So Earth is a sphere, and then you put a cube around it. And then if you have any point on the sphere, there'll be one corresponding point on the cube, right? So you just keep tracing out of your, and you have a point on the cube, there's one on the sphere. So that's fine. Now you have, instead of having a sphere, you can put everything on a cube. It's probably not the nicest projection that you can have. But in principle, then you can just, if you want to, I mean, one thing is just how do you make a nice regular grid on a sphere? It might sound easy, but in cosmology, people spend like entire careers probably constructing really nice grids on the sphere, etc. And Google wanted to do something that was fairly simple, fast, and could be used to do some fast computation. And so if you just make pixels on this cube and project them back to the sphere, I mean, that's one way to do it. You'll have some slightly odd-shaped pixels, but they'll also vary very much in size around close to the diagonals of the box compared to close to the equator. So one way to kind of get around this is to do a little transform before you do this. So if you have here, now we do like a sketch in 3D, because this is my hand drawing and I don't do 3D. So we have pixels here that we just divide the line into small segments, and then we could project it directly back to the sphere. That would give us this very big area distortion. So the simple idea was to just make an intermediate step where you transform And this is what they call an S2 cell in the C++ library. So a cell is like one of these pixels. Now there's this thing, well, if you just have the sphere or the cube around the sphere and then you project everything, then you just have 6 pixels. Like there are 6 sides on a cube, so it's a pretty coarse pixelation of the sphere, you would say. So of course the next step is to do a quad tree kind of construction. So you subdivide each side of the cube into 4, and then you can subdivide each of those into 4, etc. You can make a tree structure. Then you just need to figure out how do I, in a clever way, index this tree and use it. And this is what they did with a 64-bit unsigned integer, saying, well, this is something that's pretty fast to use on a modern CPU. If you want to compare them, etc., it's basically the fastest thing you can do. And well, you use the first 3 bits to identify the cubed side. I mean, you even have a couple of numbers extra, right? You just need the numbers 0, 1, 2, 3, 4, 5. Then you have all the sides. So that takes 3 bits to do that. And then if you do, for one of these sides, you divide it into 4. So you have 4 new pixels. Well, you need 2 bits to represent 4 pixels. Then you subdivide it again, you need another 2 bits, and you subdivide again, you need another 2 bits. And you can keep doing that until you run out of 64-bit int. So that's at level 30. So you spent 3 of them in the beginning, and then you use 2, 2, 2. So if you do 30 of these, then you have 63 bits. And then the last bit is kind of like a control bit, which is 1. If you have something at another level, then the 1 moves up. So the last bit that you see that's non-zero is a 1, of course, it's binary. And then that determines which level are you at. So it's very quick to figure out which level of the tree am I in. It depends on, in your 64 bits int, when is the last digit, the last 1. And just illustration of what are these. So far everything is like the C++ code and the RCPP code is in a package called S2, and that doesn't have a nice interface or anything. And then I've been working on the interface in this extension to our SpatStat package. So that's where there is an interface, and that's very much being changed around. So if you want to play with this, your code is probably not going to work a couple of months later. But you feel free to do something if you like. But if I looked up the GPS coordinates of the wild gallery here in Brussels, and then I asked what's the cell string here, and we can see apparently Belgium is on the 3rd cube phase. I mean, this is computer scientists counting, so this is a brief, everybody see that. And here we then have a 1. So once we've gone into the cube phase that contains Brussels, then when we do the next 4 splitting, then we're in the first one of those. And then if we look at the entire precise string, then it's like you go to the first one, the fourth one, third one, I get confused with the numbering. And then how do we like number the 4 different pixels? Like should it be 0, 1, 2, 3, or which order should you do it? And here they decided to use like a Hilbert space filling curve. So basically think about the red, there are like 4 red corners or these things. They are centers of pixels. So you have like a big pixel up here, and then you divide it into 4 and get 4 new centers, the blue centers here, or 4 new pixels. And so the enumeration of these is such that you follow this curve along all the time. So you have a space filling curve. So if you go to the next number, it's always something that's spatially close to where you are. Rather than what we know from doing matrices or whatever, you fall over the edge and jump all the way back and whatever. So here you get spatial locality in the index. Of course, the other way around is not true. Like, take 2 locations here and here, they're close in space, but they're not close on the index. Of course, like there's not a bijection between them. You can't do that. So that's how they made this S2 cell thing. And what do they look like at different levels? So I have something called S2 covering, where basically I'm saying I want to cover the entire Earth with cells of this level. And all of these functions are something that's just calling an underlying C++ function. So I mean, I've just figured out how does the library work and made some interface to R. I didn't program any algorithms at all. So I just did a basic plot of the level 5. And this is what the pixels look like. And you see they are like fairly even sized, but they're not homogeneous in their like if you look locally around them, you can find the corners of the cube, right? There's a side going on here and down here somewhere and down. So you see this is like a corner of the cube. So that's different than the other, looking slightly different than the other pixels. But it's the area of each is fairly similar. So this is basically what's underlying in this library. I could also plot it interactively so we can move around things. Unluckily, I had to go to this Mac thing. My computer couldn't be. So I lost the Earth behind. So this is like there's an Earth in here, like a nice continent. This is actually, so I know where we are. This is the North Pole. This the most important country. Denmark is somewhere around here. No, Belgium is down here somewhere. And this is like zooming into the wild gallery. So the wild gallery, the first like top level was this 2 or whatever it was, and then a 0 and whatever. So that's zooming into where is the wild gallery. So the important part is also if you want a location on Earth, then as you go along the 64-bit integer, you get a more and more precise location. So you can stop at some point when you say, okay, I'm down to meter precision or whatever you like to. And if you go all the way to the end, you have a pretty precise thing. That's the key for the next slide. So apparently I did something to my markdown here. But basically these cells, it's just, we keep reminding ourselves exponential growth is really fast. As we go through this, we can see, well, you start by a sixth of the Earth, and then when you're at level 30, you are less than a square centimeter. So a 64-bit int can index every square centimeter on Earth. So you can have as much precision as you sensibly like on a global scale. And this is just briefly, so if we want to use this as a spatial index, I guess ideally this should be going on in a database. I'm not using databases, I'm just using R and stuff directly in R. So I basically needed to make a small database in R. And what I did was use a hashed environment. So take all the, like if you have a list of like all the world cities I used here, 43,000 cities, and then just record these unique identifiers, the 64-bit ints for these at all levels, and then make a hashed environment where the name of the variable is this unique identifier, and then you have the value are the indices that have this identifier. So if you look at the identifier for like a big cube face, you have a lot of cities that have that identifier, and when you go all the way down, you have a unique city that has that identifier. And then you can look things up, etc. And then one thing that's also pretty clever is there's a fast algorithm for covering any reasonable geometric shapes on Earth or on your sphere. So I've made a spherical cap, so that's like a circular region on the sphere. And they say, I want to cover this with these S2 cells. And then it automatically runs through different levels and tries to find a reasonable fast covering. And this is a bit small, but this is a circle around Brussels that's been covered by these cells. So we see that it uses big ones and then also a lot of small ones. So you use the multi-level structure of the index. And then of course you can look something up very fast in this index. Like if you want all the world cities that are within this disk radius from Brussels, then these are all the blue cities. And sometimes when you're lucky, this says 0, 0, 0, and sometimes it's of course incredibly fast to look something like this up in a hashed environment. And then I have 1 minute left, half a minute left. I'll just say, well, you can also approximate, of course, complex polygons or whatever you like. This is a polygon of Australia. Anybody recognize it? I guess this is Tasmania down here or something. We have a finer, now it looks a bit more like Australia. I guess Tasmania might be here, and then some other Antarctic island there. You can also do interior coverings, then it looks even more like the right shape. And other cool stuff you can do is to work with actual spherical geometry. So here's like 2 polygons on the sphere, like they're in their lat-long coordinates, they're just squares or quadrangles. And then, when you do their intersection, of course, you need to be careful because it's spherical geometry. It's something that has 6 points. It's not just a new square when you have 2 overlapping squares. So if you look directly at like a simple lat-long thing, you just get a new square in the middle. But the right thing is to get this intersection, and of course the union is easy. And then I don't have more time, I guess. An ideal way to implement, like if you have a C++ library and you put the source code in an R library or R package, it's really nice to use this RCPP modules. And I tried that for a long time, and I ended up with segmentation faults, and apparently this Google code has some strange memory management that doesn't do things the way that other C++ libraries typically do them, and I'm not a C++ guru in any way, so I just had to give up. I saw that RStudio bomb thing every time I did anything. So unfortunately, I can't do that, but yeah. Thank you for your attention. So you mean finding if you take the centroid of each raster and want to find the S2, so no, they're very fast to calculate the cells themselves. I think, and I even here in R have the problem that you can't have 64-bit ints in R, so I have to convert them to the hexadecimal representation, have them as a string in R. But with 1 million entries, it takes less than a second still to get them all. And I think most of that time is spent copying back and making it back to a hex representation string thing. So if you want to work with the 64-bit int, that's still fast for 1 million points.
Other questions? Now is your chance.
Now it's your chance.
Cool. I have many, but
yeah.
later.
We'll take them later. Yeah, that's good. Yeah.